Okay, let's get started. I haven't had a chance to look at your exams yet, so I have that fun for this weekend, hopefully, to get that finished. I wanted to begin today. Well, I guess I should also mention that the Chapter 5 homework is up. It may have to be pushed back. I don't know where we'll be by like Monday, but it's due sometime early to mid next week, but that may get pushed back just depending on where things are at the end of today or at the end of Monday, how it's looking. But I wanted to go back to Chapter 4 to finish up, at least one example problem involving friction, and we'll be doing more example problems as we go through Chapter 5. It'll be one of the forces that appears over and over again. But we sort of introduce the idea of kinetic friction. Kinetic friction means when an object is sliding against a surface, so there's grinding between the surface, like I'm pushing this along the table. If there were no force pushing back against the direction I'm pushing it, then it would keep accelerating, right? Because there would be a net force along the horizontal direction. But we can see there's got to be a kinetic friction force, and it's called kinetic because the two surfaces are moving against each other. Of course, it depends on the materials that's in this coefficient of kinetic friction, mu k, k for kinetic. And, Giancalli calls this the normal force. So you could call that Fn to use Giancalli's notation there. It depends on how hard the two surfaces are pushing against each other. So if you have a very heavy object on a surface that's sliding, there's going to be a lot of friction. Or even if I have a light object, but I push down on top of it, I'm going to increase the friction by increasing the normal force that the table has to push up with to keep it from falling through the table. Okay, so that's the kinetic friction force. Simple, maybe the one surprise, and hopefully you found out this was roughly true when we were doing our friction lab this week, that it's roughly independent of the surface area. That's not exactly true. Otherwise, drag racing cars would never have big tires instead of thin tires. It wouldn't matter, but it's not as big of an effect as the kinds of materials it's made out of and the normal force. So don't think of this as a fundamental law about the friction force. We also just barely talked about the static friction force, and there are kind of two regimes for the static friction force. One of them is easily overlooked because sometimes it doesn't appear as much in physics textbook problems, but then when it does, it's kind of a surprise. That's when static means the two surfaces are not moving with respect to each other. But if I push with just a little force on this side, it doesn't move. And that means there must be an opposing force going in that direction to make the net force 0 and no acceleration along that direction, because the normal force and the weight force aren't really helping at all in the horizontal direction. And therefore, there's a friction force which balances out the applied force. So if I push with a tiny force, it pushes back with a tiny force. Push with a medium force, push it back with a medium force. If I push with too big of a force, it starts to break free. But as long as it doesn't break free, one law that you might write is that the friction force opposes the applied parallel force, and that may be from my finger, maybe from gravity. If something is sitting on a plane and it's just not sliding, right? I haven't tilted it up enough to cause it to slide. It's just sitting there. Well, gravity's trying to pull it down. Why isn't it going down? Because friction is opposing the component of gravity along the direction of that. Now, the law that you'll see appear, just not because it's the one that normally applies, but physics professors like to write laws that are about when will it break free? In other words, how hard do I have to push before it breaks free? And then we're talking about kinetic friction. It's no longer static friction. That is what, so this Fs, when we write down Fs max, that's the maximum static friction force that can be exerted by the friction force before it starts sliding. And then we shouldn't be talking about static friction anymore. Okay. How hard can it hold on before it breaks free? That depends on the materials again. That's that coefficient, this time of static friction, mu s. And it depends on the normal force, right? If I have a really heavy object, there's a big normal force. Of course, I'm going to have to push a lot harder to get it to budge and start sliding. So that law that looks superficially like the kinetic friction force law looks a lot like it, but the way we apply it is very different, because in one case, the friction force doesn't care if you're moving slowly or quickly or anything. It's kind of the same force law. But this one only applies to when it's just about to break free. Still sticking, but if I pushed any harder, it would start moving, and then we wouldn't be talking about static friction anymore. Okay, so let's do the problem, and I sympathize if you don't have this worksheet with you anymore, but this was the last one on a multi-page worksheet that we were working our way through in chapter 4. It was several pages stapled together, but we're not going to work on it together. I'm just going to talk about the solution here as a group using my solution. So here's the setup. We've got a box sitting on our famous inclined plane, inclined at a 20-degree angle to the horizontal. And for some reason, I was really in the mood for 20s this day because there's a 20-kilogram box sitting on it. And we are told that the coefficients of friction between the box surface and the plane surface, the static coefficient of friction is 0.2 and the kinetic coefficient of friction is 0.1. So that means I can find out something not only about how much friction force there is when it's sliding, but how hard I have to push to break free. Okay, that doesn't mean it's always going to be super easy, but we'll see how it goes. This is, the inclined plane case is sort of the worst case scenario. So you're seeing the most difficult kind of problem. If something were horizontal, it actually would be much easier than this one. So first question here is, what is the minimum magnitude force applied to the box in the direction parallel to the plane and up the plane? Okay, that means I'm pushing along the plane, but trying to push it up the plane. If the box is sitting there, how hard do I have to push? I push a little bit harder, a little bit harder until it starts budging up the plane. How hard do I have to push to get it moving? There's some minimum force I have to push with up the plane. And then there's a little follow-on question that if that force is maintained, then what's the acceleration? Once it budges, it's going to start accelerating up the plane, and there's a little kinematics problem that we'll do at the end. But let's just concentrate on that first question here. How hard do I have to push in the direction parallel to and up the plane to get it to budge, to stop moving? What's that minimum force I can apply? So let's draw a free body diagram here. Of course, there's the usual suspects. The weight force is going straight down to the center of Earth. There's a normal force from the plane, which would be there even if there weren't friction. Again, Giancalli would call that Fn. I should probably start switching to Giancalli's notation. Just depends on which book you use. And then I am going to be pushing up the plane, and I'm interested, what I'm trying to draw here is a situation where I'm pushing with the minimum force that is just about to make it budge, and it's just barely hanging on. So if I pushed any harder, it would break free and start going up the plane. But I'm just right on the edge there. It's still sticking. It hasn't broken free yet, but this is supposed to be a picture of it's just about to break free. Now, the question is, which way does the friction force point? It's easy when you're talking about kinetic friction, because whichever way the object is sliding on the surface, the friction force is pointing back the opposite way. You can always see which way it's going, just depending on the motion. When it's static, nothing's moving, and you got to think a little bit. In this case, it might be up the plane or it might be down the plane. Friction forces are always parallel to the surface. But is it up the plane or down the plane? Now you can see my free body diagram. I've got it going down the plane. Anybody want to make an argument for why the friction force isn't pointing up the plane? Yeah. Well, the object isn't moving in my free body diagram. The situation is I'm pushing up to but parallel to the plane. And if I pushed any harder, it's going to break free. It's still just barely sticking. It's barely hanging on. So if I pushed a little bit harder, friction couldn't hold on anymore. So you can imagine that friction is trying to hold it back, and it's holding back as hard as it can. It's pulling in the direction down the plane. And if I push any harder, it can't pull back any harder, and it breaks free and goes like that. But it's not so obvious, because if I, just had, here's a more normal situation or less going on. If I just had a box and I put it on a plane, well, let's suppose friction's big enough, it doesn't start sliding, right? It's just kind of stuck to the plane. It's not a very slippery plane. And we drew in the forces. Well, of course, there's a weight force going down there, mg. Of course, there's the usual normal force. In this case, I'm not applying a force, so there's no pushing force. Which way is the friction force going to be in this case? Yeah. It's going to be up the plane. I mean, if it were down the plane, it looks like all the forces are sort of adding up in that direction, and it wouldn't be stuck. It would be accelerating down the plane, right? There's nothing to oppose. The gravitational force is already trying to pull it down the plane. And so to oppose that, we have to have a friction force that's up the plane. So in that case, we would say, oh yeah, there's a static friction force that's up the plane. But our situation isn't like that. I'm pushing, I don't know what I called it over there, but I'll call this F push. I'm pushing up in that direction with a force that is just about to break it free. So friction is holding on and trying to pull it back as best it can. And if I push any harder, it can't pull back any harder. So friction is pulling it in the direction down the plane. And if I'm drawing a picture where it hasn't budged yet, we're talking about a static friction force. And if it's just about to break free, we're talking about the maximum static friction force that it could possibly exert under those circumstances. So let's go back to this picture now. Okay, so that's why I've got my static friction force going down the plane, because friction's trying to hold. I'm about to push it up the plane. It's about to break free. So friction's trying to oppose that motion as best it can. And the claim is, because it's about to break free, I'm justified in labeling this as the maximum static friction force, whose formula is mu static times the normal force. Mu static here is 0.2 was just given. Those are dimensionless quantities, just a pure number, 0.2. And the normal force I don't know yet, or you could label that as Fn if you want to follow Giancoli. That's probably a better notation, because just N looks like newtons. It's not 0.2 newtons. What I mean is 0.2 times N, probably be better if I labeled it as Fn. Okay, there's my free body diagram. Of course, I want to apply Newton's second law, but I got to remember, I'm drawing this in a static situation. So nothing is accelerating in my picture. It's stuck. It's on the edge of breaking free, but it's just still sitting there. Yes. The other one that's not in the diagram, that's for when it's broken free and it's actually sliding and the two surfaces are grinding against each other. And that's not necessarily relevant to this first question. We'll find out that it's relevant to the stuff that I kind of erased here, that's the follow-on questions. But I want to know that minimum force that's going to make it break free. And we always do the same thing. We don't imagine it having broken free. We imagine it being on the edge of breaking free. And if I pushed any harder, it would break free, but I'm still talking about a static situation. Nothing is moving in this picture, and therefore all my acceleration components are 0. Now, I don't know what components are because I haven't put any axes in there. But of course, that's the next thing I'm going to do, because I'm going to apply F net equals ma components. So the next thing to do is to choose some axes. In this case, again, it will be, because so many forces are aligned parallel to and perpendicular to the plane, it makes sense to make your axes parallel to and perpendicular to the plane. So I'm taking plus x to be in the direction up the plane, plus y perpendicular. And all I'm going to do is write down F net y equals may and F net x equals max. You'll see why. You might say, well, I want to know F min, right? That's how hard I have to, the minimum I can push with to barely make it break free. I would like to know that force, and it's involved in the x component. So why not just go for it and do the x component? So let me click down here and show you what that looks like. When you write that down, that's going to involve the static friction force, and that depends on the normal force. So I won't be able to go anywhere with the x components until I've dealt with the y components, which is why I'm doing F net y equals MAY. But even if you went the other way, you'd find out quickly that you need to write this one down too. Okay, so in terms of components, these two have 0 y components, right? They're along the x direction only. N is all along the y, so it comes in with a plus sign, and then I have to find the component of the weight force along the y direction. So that's 20 times 9.8 times the cosine of 20 degrees. And that's equal to MAY, but AY is 0 because, again, I'm imagining it's about to break free, but it hasn't broken free. Okay, it's a static situation. That allows me to solve for the normal force. So that's good. We'll use that in just a second. Okay, so I figured out what the normal force is. Before, when we were talking about frictionless planes, we didn't worry about it so much, but now it's crucial because the normal force appears in something that's going along the x direction. That normal force appears in that 0.2 times the normal force n. So in terms of x components, there are 3 forces that have non-zero x components. F min comes in with a plus sign. Mu static times the normal force, and we now know what the normal force is. That comes in with a minus sign. And the gravitational force is more or less in the negative x direction. You have to go along the negative x direction and going from tail to tip. And that involves a sine of 20 degrees over there. Okay, so there's some details to sweat here, but moving through, you'll notice now that I've put that stuff in, the only unknown here is F min. And so I can solve for the minimum force I have to push with. That's where I'm right on the edge. You know, maybe a little thermal vibration happens and it breaks free. So that's the minimum force I have to push with. If I went any over that, it would definitely start sliding. This is right when it's about to break free. Questions on that first part before we go to the other questions? Okay, so that was all static friction. And notice it had to, you've got to use that law in the context of about to break free. Also, now, here's a second part. If that force is maintained after it breaks free, what is the subsequent acceleration and what's the box's speed after it's moved 1 meter? That sounds like a kinematics problem, 1D kinematics, just for fun, for old time's sake. Okay, so I need a new free body diagram now because it's not just about to break free. Now it's moving along. You know, static friction isn't involved anymore. Once it's broken free, we're talking about kinetic friction. So, did I not do a different free body diagram here? I guess I did. Let's draw it on the board. Let me move these windows over so we can see a little bit better. Okay, so now it's about to, it has broken free, right? It's moving up the plane. I found out how big this is. I think I remember it was 104 newtons. That's what we found out that minimum push was. And now the question is, if you maintain that minimum force, but now it's moving, you'll find out the normal force is exactly the same as it was before. But what changes is static friction is not going along that direction anymore because now it's grinding against the surface. I should be talking about a kinetic friction force that's opposing the direction it's sliding, right? And the formula for that is mu kinetic times the normal force. Okay, and our mu kinetic in this problem is 0.1 times the normal force. Okay, so, you know, looking at that and going back to, let's see how that compares with what I've got written down there. I should have technically drawn another free body diagram, although it looks very similar. The names of something has changed. The 104 is coming from this pushing force, and I'm doing F net y equals MAY in this case here. So F net x equals MAX for the same axes I chose before. So the 104 comes in with a plus sign. The friction force, mu static times the normal force, comes in with a minus sign. You could check if you wanted, but the normal force doesn't change because nothing with a non-zero y component changed in this. So F net y equals MAY is exactly like it was before. So the normal force doesn't change. And then here is the X component of the weight force. It also comes in with a minus sign. And now that is equal to the mass of the thing in the free body diagram times the unknown acceleration, which again, I can't see because of these windows here, but there's an unknown AX there. And notice I know everything in that equation except AX. So I can solve for AX, 0.921 meters per second squared. Everything was in SI units. And then I can do my kinematics problem. What is the box's speed after it has moved 1 meter? So it breaks free. I'm pushing with that minimum force the whole time, and it moves 1 meter. What's the box's speed? What kinematics equation would you go to? Describe it any way you want. Which of the 3 kinematics equations we talked about would you jump to there? Yes. Yeah, the squared one, because it doesn't involve time. We don't know anything about time. We don't want to know anything about time. We do know something about velocities, so it seems to make sense there. So here I know this is kind of a crazy, oops, kind of a crazy path through the problem, but it made sense when I was, oops, I didn't mean to do that. Made sense when I was working my way through. So there's that kinematics equation right here. We know AX. We know we want delta X to be 1 meter, and we want to find what Vx final is when Vx initial is 0. So we plug those in, and you can figure it out. Every time I go back to this, it moves these windows back again. 1.36 meters per second. Same old stuff with our kinematics. Any questions on that example? I know it's a first one. They're not really going to get any more complicated than that one. I mean, I can maybe think of one other context that we'll see in chapter 5 that might seem more complicated than this, but when things are on an incline, that's about as bad as it gets. And you just have to be careful about drawing your free body diagrams. Any questions before we move on to chapter 5? Good. So you'll see the friction problems that I removed them from the chapter 4 homework, and now you have a chapter 4 part 2 and chapter 5 part 1. Chapter 4 part 2 is just 2 problems that I moved. There actually wasn't much having to do with friction there, but there's a lot of other problems that are chapter 5 problems that have to do with friction. So we'll get plenty of more practice. Okay, couple of warm-up voting questions here, just to get your intuition, because you, or maybe you don't have the intuition, but you remember it from the reading. Way back when we were first talking about kinematics, back in chapter 3, two-dimensional kinematics. Here's an object. At one instant of time, it's moving vertically, and a little bit later, it happens to be moving at an angle to the vertical. It's going at the same speed, right? The length of the velocity vector is the same. Which of the acceleration vectors shown over here, A through D, best represents the direction of the average acceleration between these times? So maybe there's an ant walking along at a constant speed. It was going up, but then it started tilting to the left at that later time. So we just know those 2 times what the velocity vectors are. Average acceleration, this is just to remind ourselves of the definition of the average acceleration. Okay, most seem ready to vote, so let's hold them up so I can get a sense if we're all on the same page or not. If you don't have yours, just do numbers or something like that. You know, the B's and C's have it. My impression is there's slightly more B's than C's. Can anybody, you know, without arguing for a particular answer, just remind me of what is the definition of average acceleration? If I wanted to write down a formula for the average acceleration vector, let me go to the board here. We wrote that somewhat in a cumbersome manner. So acceleration vector, but average. Anybody remember how to compute it? Yeah. Yeah, it's just change in the velocity vector over the change in time. And notice, when we talked about scalar multiplications, the delta time is just a scalar, and 1 over delta time is a scalar. Scalar just means a plain number. It doesn't have any direction to it. There's no direction in space to time, right? So we're thinking of this as a positive scalar multiple of this vector. So if we just want the direction, we could say, hey, you multiply by a positive number. It doesn't change the direction. It rescales how long it is. But all these have different directions. So we just want to find the direction in this problem of delta V. Okay, let's try to draw the picture here. So at one time, we'll call this V1. When it was down here, that's what its velocity vector looks like. Later on, it was over here, and it was tilted up like this, V2. This wasn't exactly like that, but it's more or less like that. How do I picture delta V back from our vector stuff? Yes. Yeah, from one tip to the other tip. And when we do a delta, it's always from the earlier to the later one, right? That's one easy way to not think about it too much. So I can remember we can parallel transport vectors. If I had drawn this exactly correct, they should, the vectors on the voting question were about the same length. So they should have the same length there. And if I draw from V1, tip of V1 to the tip of V2, that's a picture of what delta V is. So in this, let's go back and look at the possible answers there. In this case, the best answer is actually the one that's tilting down and to the left a little bit. You know, a fair number of you, I admit there's sort of subtle differences there. So you guys who were voting for B's and C's, you weren't terribly far off, but in this case, if you bring this up there in your mind, you're going to see it has to go down and to the left a little bit. Here's how I might do it, just constructing the same thing. So putting them with their tails at the same place, and then the difference between V final and V initial points between from one tip, the initial tip, down to the final tip, which is down and to the left there. Okay, that's going to come into something that's in the second voting question. So we'll talk about the details here, but this is just based on either your intuition from that problem or from the reading. An object moves in a circle at a constant speed. We're going to be talking about uniform circular motion. That means motion in a circle at constant speed. At the instant shown, it's moving upward. So it's that dot that's on the right-hand side of the circle. It's going around at a constant speed. And we're just talking about a moment when it's right here, passing that point. At this instant, which direction does its acceleration point? Either thinking about that previous problem, which might still be a little bit obscure, or from the reading. I just want to get a sense of how people remember or don't remember this. All right, let's see a vote if you've got it. I know I'm rushing you a little bit. I'm seeing lots of C's, a couple other votes mixed in there, but mostly C's to the left. And yes, the answer is C. It's to the left at this point, which the first time you see it, you know, if you hadn't taken a physics course before, which many or most of you haven't, that's a little bit non-intuitive. It's going up, but it's accelerating to the left at that point. So we want to make sure that that agrees with our definition of acceleration or average acceleration. And so let's try to unpack that a little bit. The correct answer is C, and most people were voting that. So let's see where that comes from. So again, we're talking about uniform circular motion. Oops, that means motion in a circle at constant speed. That's what the uniform part means. It's going to be important because we're going to talk about the motion of the Earth, the moon around Earth, and Earth around Sun. And though they're not exact circular orbits, they are pretty circular and they are pretty uniform. The speed of the moon with respect to Earth doesn't change a whole lot through its cycle. Okay, so here we could imagine something moving in a circle of radius r, and at some time it's here, moving up and to the left. And as we talked about earlier, if you're following a path at any instant, your velocity vector is always tangent to the path. So the velocity at that time is tangent to the circle. And our goal is, at this point in time, to figure out for this object, what is the direction of the acceleration at this instant, and what is the magnitude of the acceleration? We're going to find out the magnitude depends on the radius of the circle, and it also depends on the speed. The bigger the speed, the bigger the acceleration. So let's quickly go through the derivation there. Some of you may have watched these videos, although it's by no means required. You're not required to know this derivation, so I'm going to, not spend a horrendous amount of time going through it, but it's pretty elementary, all the steps in here. So we're talking about the acceleration vector, and that's like delta v over delta t, where we just take a tiny little change in time, okay? And we're going to think of the 1 over delta t as scalar multiplying the delta v, okay? So let's first talk about the direction of this acceleration vector. And to get that, I'm just going to ignore the 1 over delta t. It's just rescaling it. If I want to know the direction, I just want to know the direction of delta v for a very small time interval. Velocity vector doesn't have time to change very much, but so here's a not so small time interval. Here's time 1 here, here's time 2 here. It's going at a constant speed, so those are supposed to be the same length vector. They're pointing in different directions. And if I wanted to know the direction of delta v, we do the construction we just did, right? Put their tails at the same place, draw delta v from the earlier tip to the later tip, right? Now, that's not going to give me a good idea because these weren't particularly close in time. We want this in the limit where delta t goes to 0, so where those two times are really close together. So let's back it up to try to get some intuition. I'm putting the times really close here, or at least close enough that I can still see the difference in the picture, but much closer than before. If I make the same construction over here, and then I imagine this angle in here getting really small, is it pretty clear that the delta v vector is going to start to become very perpendicular to the two v vectors? Whichever way it's going, delta v is going to be at 90 degrees to it as I make let that angle get small. It's not true up here, but it is true down here. So it's in the direction perpendicular to the two vectors, and at this instant, that direction would be toward the center of the circle. Perpendicular to the direction it's going is toward the center of the circle. I know away is perpendicular too, but you can see from the picture here that it's toward the center of the circle at that instant. So that's the first thing we wanted to find out. What's the direction of the acceleration in uniform circular motion? Toward the circle center, and we call it centripetal acceleration. Sometimes people say centripetal means center seeking or center pointing, like it points towards the center of the circle, or it's going toward the center of the circle. But centripetal acceleration is not anything special. It's just a special case. It's just the acceleration of something moving like this at constant speed. It's not like it's something different than overall acceleration. There just happens to be a special name in this case. All right, now let's think about the magnitude of the acceleration. And again, we're going to start with the definition, but let's just take the length of both sides of this. So if I take the length of the acceleration vector, notice that what I want to do is, for a very short time, take the length of this velocity vector. In other words, how long is it? And the name for that is just v. Oh, I'm sorry, not the length of the velocity vector, length of the change in the velocity vector. So here's the change in the velocity vector there. That's not a particularly small time, but let's now label some things on the diagram in terms of vectors. Okay, I'm going to turn this into just a plain old triangle, but for right now, it's a little bit of an enhanced triangle because it doesn't just have plain sides. The sides are vectors. Here's another triangle I'm going to form over here. I'm going to say at time t1, r1 is where it was relative to the center of the circle. It was there. And at time t2, we'll call r2 where it was at this relative to the center of the circle. Okay, and I can draw a similar kind of enhanced triangle that's made out of vectors. where I say R1 and R2 have their tails at the same place, and delta R is the displacement between those two times. And we're just going to compare these two triangles, but since they have vectors on them, the first thing I'm going to do is just take the absolute value, the length of each vector, and make a standard triangle. Okay, so let's call that angle theta in between time 1 and time 2, and let's notice that it's the same angle in these two triangles there. When you rotate through an angle theta there, this velocity vector rotates through the same angle there. Takes a little bit of thought. Okay, so getting rid of the vectors now, I'm just taking the absolute value or length of both sides. V1 and V2 have the same length. We called that V, just the speed that it's moving around the circle with. R1 and R2 have the same length. That's just the radius R of the circle there. And let's call this delta V and this delta R. Now, if you have two isosceles triangles, triangles that have two sides of the same length like this, and they have the same angle in between those two equal length sides, that's one case of triangles that are called similar. Similar triangles means one is just kind of an inflated version of the other. It's zoomed out or zoomed in, it's made bigger or smaller, but they could be made to lie right on top of each other. Okay, and one thing that you learned back in your geometry course or fraction of a course way back when is that if you have similar triangles, if you take the ratio of two sides in one triangle, that's the same as the ratio of the analogous sides in this other triangle. In other words, if this side is half the length of this, then this side would be half the length of this. That's what this relationship is saying. And that allows me to trade out this magnitude of delta V for a magnitude of delta R. Okay, and when I do that, so that's telling me I can solve for the magnitude of delta V is V over R times the magnitude of delta R. And I'm just going to substitute into the thing we want there. So when I plug that in, I get a V over R times the magnitude of delta R over delta T for a very short time. If I say over delta T, I move through a tiny little delta R, and I've got that delta R over delta T. Isn't that delta R over delta T? This is how far it moved, and this is how long it took. So this is the speed it's going at, delta R over delta T. Okay, so this is another factor of V sitting right here that I'm circling, okay? V over R times V, and that simplifies to V squared over R. And honestly, you know, the point of me doing this is to show you that it's not rocket science we're doing here. Every step is elementary, but it's a little bit complicated when you string them all together. For you, you should remember that takeaway, V squared over R. When something is moving in a circle of radius R, at speed V uniformly, that means at constant speed, the magnitude of the acceleration is V squared over R, and the direction of it is at every point towards the center of the circle. Okay, end of derivation. So now let's just think about this a little bit. The acceleration as it's moving around at constant speed when the object is here points to the left towards the center of the circle. Here, toward the center of the circle. Always the same length. If it's moving around at constant speed, V is the same and R is the same, right? So V squared over R is the same. Always the same length acceleration, but the direction is changing. So we call that centripetal acceleration, but it is just the acceleration. There's no reason for that special name to, you know, make you think that it's something different than some other kind of acceleration. It is the acceleration. Okay, let's do an example. Imagine here an astronaut in deep space. I'm saying deep space because gravity complicates things a little bit, but if I take this little mass that I've got on a string and we forget about the fact that there's gravity in the room and I swing it around out in deep space, I'm on a spacewalk and I'm swinging this around at a constant rate, okay? That's the picture we're thinking of here. And let's look at the numbers that are given. Okay, so it's a half kilogram, unlike my mass, half kilogram is pretty hefty. Half kilogram ball attached to a 0.7 meter long string, a little bit less than a meter, right? She spins it in a circle at 80 revolutions per minute. You may have heard of RPMs before. That stands for revolutions per minute. That means in 1 minute, it goes around 80 times, 80 complete revolutions per minute. The first question is just, is the ball accelerating during this process? Dylan, you just shook your head yes. How would you back that up?
It's always changing the direction and acceleration components of the direction and the magnitude.
Yeah, I mean, that was the whole point of what we just said. If something's in uniform circular motion, yeah, it's accelerating at every instant. Even if the acceleration weren't changing direction, we showed that there was an acceleration at every instant, but it is changing all the time too. But yes, it's in uniform circular motion. So the answer is yes, it's accelerating. Okay, then the second question is, what's its acceleration? Well, the direction is always going to be toward the center of the circle. That's easy. At every point, the acceleration of the object is pointing inward along the string direction, if you like. What's the magnitude though? Okay, the magnitude, well, all we have to go to is v squared over r. It's in uniform circular motion. And hey, one thing's easy. I know r, it's a 0.7 meter long string, and that means this radius, I don't know what happened to my graphic there, but that's 0.7 meters. So we know r, halfway done. Unfortunately, I don't know v. And this is something that's going to be very important, or it will come up quite a bit. When someone gives you an RPM value, in fact, you're going to see this very thing happening in lab next week. You're going to measure an RPM value, and you want to translate it into a speed, right? Doesn't it seem like the faster it's rotating, the more RPMs it's rotating with, the faster its speed would be. So somehow that RPM value is telling me information about its speed, but I've got to figure out how to get it out. So let's talk about how to do that here at the board. Here's the trick. Well, can anybody tell me how they might approach it just before I tell you my way of explaining it? It's moving at a, oh, okay, go ahead. Yes. Yeah, the 60 is important to us, right? Revolutions per minute, 1 minute or 60 seconds. It seems like I might be able to use that 60 seconds. And we are going to use that. It's going to make our life really easy. Because the speed is constant, it's not changing with time, right? If I'm going at 2 meters per second, and I didn't know my speed, right? If I'm going at a constant speed, I can use any distance I move divided by the corresponding amount of time, right? To get 2 meters per second, I could say, oh, I moved 2 meters divided by 1 second. Or I could do 4 meters divided by 2 seconds, right? As long as my speed is constant, I can use any distance I want divided by the corresponding amount of time. Sometimes I call that the distance over time trick. Of course, it's got to be that you're moving at constant speed, but that's the whole point of uniform circular motion. This thing's not changing its speed. And as was pointed out, a convenient time, since in this case we know it's going 80 revolutions every minute, and I like to use SI units, so I'm going to change a minute to 60 seconds. A convenient amount of time to use is going to be the 60 seconds. And then we're just left figuring out what distance does it move along its path in 60 seconds. And how would I figure that out? Yeah. Yes, it moves through 80 revolutions. So the distance it goes is 80 circumferences. And the circumference, hopefully it rings a bell, is 2 pi r. That's how I relate it to the radius. We're given the radius here. So in 60 seconds, it goes through 80 revolutions. That means it moves a distance of 80 2 pi r's. And we know r, and therefore I can calculate the speed. So I sometimes call that the distance over time trick. It's not a trick, it's just a method or way of thinking about it. Okay, so here's the, again, repeating it, the distance over time trick. 80 circumferences in 1 minute, because we know what happens in 1 minute, that the convenient amount of time to choose is 1 minute. And then you have to think, what is the corresponding distance? So I get 5.86 meters per second. That's how fast it's moving at any instant. Velocity is changing, but its speed is not changing. And then I can just plug in A is V squared over R, right? That's how fast its acceleration is. That's the rate of acceleration, 49.1 meters per second squared. So that's almost 50. That's about 10 times little g. So it's accelerating quite a bit compared to the free fall acceleration, which seems pretty fast already. So, but you're not a coin, so you don't have to worry about how fast it's being yanked around. What is the string tension that causes the acceleration? Okay, so we figured out the acceleration, direction, and magnitude. Now the question is, well, that string seems like it's got to be taut. What's the tension in the string? How much tension is required? And to do this, we're going to set up a free body diagram, right? Tension's a force. It's going to come into a free body diagram. We know the A part of F net equals ma. Now we're just going to use it to figure out a force. So again, let's go back to the board just so it doesn't go too fast on here. Let me draw a little cartoon here. Pretend that's a circle, and here we are at 1 instant in time. Okay, so here's my mass. What was the mass in this case? Half a kilogram, right? 0.5 kilograms. And here's a string that's under tension T. So what I'm going to do is, sometimes I don't draw my free body diagram on top of the picture. So I'm just going to say, let's draw a free body diagram for this thing at that instant. So here's my 0.5 kilogram blob. We're in outer space, so there's no weight, right? This is in deep space. What forces are acting on it? Well, certainly the string is attached to one end of this. And at that instant, the instant that I draw on the picture here, here's what the tension is pulling in the direction the string is connected, right? And I don't think there are any other forces acting, right? We're in deep space. There's no gravity. There's no normal force. It's not on a surface. There's no friction force. So there aren't any other forces. The string is the only force on it. So there's my free body diagram. That's nice and simple. Since there's only one force, why not take plus x to go toward the center of the circle at that instant? Remember our rule of thumb, if you ever know the direction of the acceleration, line up one of your axes with that direction. We know the direction of the acceleration is toward the center of the circle. That's what we just figured out. So, and then, well, boy, there aren't a lot of choices. Sum of the force x components equals max. The only force that comes in here is just the T that comes in with a plus sign. The mass is 0.5, and the acceleration, I've forgotten, but I'm going to bring it up here. 49.1 meters per second squared. So at this instant, we said, normally you don't draw accelerations in a free body diagram, but it's okay to put it next to it. It's accelerating down and to the left at that instant at 49.1 meters per second squared. That's all x plus x. So this is 49.1 in SI units. Okay, so that gives me something a little bit less than 25. Let me go back and share the screen again. Okay, so sum of the force is ma. We did our free body diagram up and to the right, and we get 24.6 newtons. Okay, that was an easy first step kind of problem because there's only one force involved. So we're going to start to slowly ratchet it up between now and Monday as I look at the clock and see that there's only 10 or 11 minutes left. Okay, so this was a case where string kept something moving in circular motion, or we could say it caused the circular motion. If it weren't for the string, it would just be shooting in a straight line, right? But the string was there keeping it moving in a circle. What types of other forces besides string tension could cause something to move with uniform circular motion? Gravity, that was an example, that gravity causes the moon to move roughly in a circle around Earth. It's not exactly a circle, but it's pretty close. And it's pretty much constant speed too, relative to the center of Earth. Same thing for the Earth with respect to sun and a lot of other planets around the sun. Some of them are a little bit more elliptical than others. There can be other forces too, right? I could be in a car driving in a circle. If I asked you, as I drive the car in the circle, what force is keeping the car being exerted on the car to keep it going in a circle? What would you say there? Yes, the what? Well, I wouldn't say the centripetal force because we'll talk about why I don't like the term centripetal force, but it doesn't really tell you which force, right? What's causing the centripetal force? In this case, you could say the centripetal force would be the string tension, right? So what is the thing? What kind of force that we've already talked about is causing me to move in a circle when I'm driving my car around at constant speed in a circle? If it weren't for that force that we can point to, I'd be going in a straight line. Yeah. Well, the direction of the wheels have to do with it, but the wheels aren't a force by themselves. The friction force, right? In other words, friction is a force between the wheels, which is part of the car, and the ground. And the ground is pushing on the car wheels toward the center of the circle at any instant in time. So as a car is rounding the top of a circle like this, the ground is pushing on the wheels in that direction. The wheels, as you might feel, are trying to push the asphalt out in the radial direction, right? It's pushing out in that direction. That means by Newton's third, it's pushing, the ground is pushing in. Okay, so there can be lots of different forces. Can more than one force be responsible for causing uniform circular motion? The answer is yes. If we'll see several cases where it can get a little bit confusing, but here's the simplest case that we'll analyze if we have time in the next 8 minutes. So here's a string. I'm not out in outer space anymore. Here I am on Earth demonstrating this, right? I'm going to put this into, watch it, it's going in a circle and it's not changing its speed. Now, the tension of the string is up and at an angle, right? The tension in the string is not towards the center of the circle that it's traveling on. The center of the circle is in the horizontal plane that it's moving. So the tension certainly has something to do with it, but what's the other force that's helping to cause this uniform circular motion? Gravity, right? If you we'll draw the free body diagram in just a second, but if it were just the tension, it wouldn't be moving in that strange way where it's not going around the string the same way it was before. So that can certainly be true. Given that more than one force can cause the uniform circular motion or might be involved in making it move in circular motion, sometimes you'll see some textbooks or students when they first learned about this, they'll see m times v squared over r and they'll call that the centripetal force. And that's kind of misleading because, well, first of all, we can see there are forces that are causing this. It's not a new mysterious kind of force we're learning about here. They're the same old forces from chapter 4 that we're going to be recycling here. And so there are 2 points I want to make here. There might be more than one force that causes it, like the tension and the gravity for that conical pendulum I was just demonstrating. But more to the point, when you do m times v squared over r, this is like ma. This is the ma part of F net equals ma. You don't put forces on this side, you put forces on this side. So I shouldn't think of this as a force. This is what happens as a result of all the forces, which are perfectly ordinary forces that we already talked about in chapter 4. We're not going to introduce any new ones, at least at the beginning. We will start to talk about gravity in a new way that's not just at the surface of Earth. Okay, so maybe I think we can talk about this conical pendulum case, which is what I was just demonstrating with that mass on the string. The idea is it's moving around on a circular path, but the string isn't along the radial direction of the circle that it's on, okay? And the first question I want to ask is, what is the acceleration? So I put some numbers in here. Suppose the angle of the string relative to the vertical is 35 degrees. the length of the string is 1/2 meter and the mass is 2 kilograms. Wow, that's a hefty mass, but okay. Strong string. What's the acceleration? Well, in this case, if I knew r and I knew v, I'd just plug into v squared over r, but I don't know v. I'm going to have to, instead, usually when someone asks you for an acceleration, your first inclination should be to go to F net equals ma, because we do know something about the forces that are acting on this. And so what I'm going to do is do that and draw a free body diagram for this 2 kilogram object at this instant. Okay, so I'm imagining it's going around in a circle that we're seeing partially edge on, and I'm going to draw it at the instant when it's just coming towards us at this point in the picture. Okay, here it is. I just drew it adjacent to there. Okay, weight force, as always, points down towards the surface of or center of Earth, 2 times 9.8 mg. And of course, there's a string force. There's a string tension. And if you can probably see, I think this angle and this angle, if you were in a Euclidean geometry class, you might call those alternate interior angles for parallel lines looking like this. Hopefully it's clear that that angle is the same as that angle. Okay, that's my free body diagram, and I can't see any other forces that are acting on it. So let's put some axes there. Why did I choose my axes to be horizontal and vertical, I mean up from the surface of Earth, rather than tilted along the string direction? What's my rule of thumb for how to choose your axes? Yes. If you know the acceleration direction, put one of your axes along that. And look, the direction to the center of the circle is horizontal here. So I definitely want one of my axes to be horizontal. So chose that. I want the magnitude of the acceleration. The acceleration's all along the x direction. So maybe let's just go for it. I'm not sure what's going to happen when I click forward, but let's hope that we're just going to go for it. And let's do F net x equals max like I've got written up here, because ax is going to be the magnitude of the acceleration, right? It's all along the x direction for the axes I've chosen. Okay, so let's flesh that out a little bit. This weight force has 0 x component. It's all along the negative y. But this tension force it's partially along the x direction. I need to find this side of the right triangle, and that's going to be t times the sine of 35 degrees. If I drew a right triangle in there, t times the sine of 35, and it comes in with a plus sign because it's pointing more or less in the plus x direction. Mass of the free body diagram is 2. I didn't draw it in here, but there's a 2. And the x component is just the magnitude of the acceleration. So I just wrote an a there, and I would solve for a, except that we weren't given t in this problem. That's disappointing. So what choice do I have now? If I could only find t, we'd be done, right? How am I going to find t? We've set up all the work to do it. We haven't used the y components, right? Let's do F net y equals may. Okay, so I'm going to try. I'm just holding on to that one, but t is involved in the y components too, so maybe I'll be able to solve for t. Okay, so this has a y component, it's negative. This has a y component, and it's positive, right? So I get a t times cosine 35 coming in over here, and the weight force comes in with a minus sign, 2 times 9.8. Why did I put a 0 on the right-hand side of F net y equals may? Yeah. Yes, because I know it's accelerating. It's in uniform circular motion. Its acceleration vector is toward the center of the circle, and that means there's 0 component along this direction. If it were accelerating in that direction, it would be blasting upward or going downward or something, but it's just staying at the same y coordinate. So of course, ay is 0. If you're sitting at the same y component, ay has to be 0. Okay, and notice the only unknown there is t. I can solve for t. I can bring this equation down, plug in my t, and solve for a. and I get A is 6.86 meters per second squared there. And I think we're just about out of time, but the next question is, what speed is it moving with? Notice we're not given that, but I can now use v squared over r is A to solve for what v is, right? V squared over r, you got to figure out what r is. R is this distance. It wasn't given in the problem, but you can do some trigonometry to figure out what r is. And so you can back out what the speed is. Okay, that's a little bit more complicated. So we're going to, on Monday, even step it up a little bit more and think about riding a Ferris wheel around at a constant speed, and think about the forces on someone's body as they're moving around in different parts of the circle. And things are going to change as you go around the circle, right? If you've been on a frighteningly fast Ferris wheel before, you may notice that you feel a little bit light at the top and it makes you worried. And then at the bottom, you feel sort of crushed down into your seat. Most of them don't go so fast that it's that exciting. Have a wonderful weekend. You can start looking at chapter 5 homework, but I don't guarantee that we have talked about the majority of it yet.